Okay. Whoa.
It's a great pleasure to introduce an old young friend, Hugo Duminil, and he's going to be TA of a course of Ensemble for our SLE. And Hugo, despite his young age, already made fundamental contribution to the area. That's back to what I said at the beginning. This area developing so fast that before ending PhD people are remarkable results. So thank you very much.
Thank you for the invitation. So, okay. I will have, I hope, corrections on my internet site, and that will be a very early draft. So if you have any comments about typos and mistakes and everything, feel free to bring them to me. Okay, so before starting, I can perhaps just summarize what we are going to do during these 2 weeks. So the first week will basically be the background, because you will see that SLE is involving tools that come from probability stochastic calculus, from complex analysis and things like this. So very wide background is necessary to start understanding that. So the 3 first lectures will be basically percolation and discrete models, and after I will during the next session I will explain rudiments in complex analysis that you will need to understand the course. In the third week, third session, I will explain Ito's formula. So I would like to know how many people already know that. Okay, so a lot, but not everybody. So that's typically what will be hard. I think that people have very different backgrounds, so we need to try to make everybody happy, but I don't guarantee that I will manage to do it. And in the second week, we will start really to handle conformally invariant processes and to try to prove things about them. And what I like with all this theory of SLEs and conformally invariant objects is that you can bootstrap information from these models to discrete models that you know pretty well, like percolation, Ising model, random walks, and things like this. So the philosophy will be more, so I had choice between explaining the technicalities of the course or trying to make you put your hands in the model and try to prove things that will be useful for, say, you will see percolation or random walks. So we will do more the second thing. We will really try to prove what we call critical exponents for percolation, for random walks and things like this. Okay, so like always when you plan to do a lecture, there is something nice to do is 10 minutes before to read again your paper and see that there is a huge mistake in the middle. So that's exactly what I did. So for people that are fast and that are looking at question 3, don't try to do it. Or perhaps you can, I don't know, but it's not true like it's stated, so I will need to explain it later. Okay, so before, I will let you a little bit of time. We are trying to do the exercises together, but before I would like to be sure that we agree on the model we are working with. So we are working with side percolation on the triangular lattice. So I'm very bad at drawing this, but so you have a triangular lattice. And every side will be black or white, so black and white, with probability 1/2. So we are at the conjectured critical point. And my goal for this lecture is to try to make you work on this critical point and try to prove things at this critical point. So as Vincent explained this morning, when you are subcritical or supercritical, you have very different behavior from the critical point. you have exponential decay of connectivities, or you have an infinite cluster that takes all the room you can imagine. But at the critical point, there is something very subtle that appears. Somewhere you are exactly at the balance point. And the main tool in order to understand this critical phase is the Rousseau-Semmelweis theorem. And what we will do, and we'll try to prove it, we managed to prove it, hopefully, but, and after try to have, say, implication of this theorem. So just to be sure we agree that the probability, you look at the probability for a rectangle. So a rectangle in the case of the triangular lattice, it's not a rectangle, it's a lozenge like this. And we look at the probability that there is a crossing. What we call a crossing is a black path of neighboring sides that go from the left side to the right side. And there is something very specific to the critical point, which is that if you take a lozenge of size n times alpha n, this probability remains of order 1, in the sense that it does not go to 1 nor to 0. So there exists universal constants, c minus of alpha and c plus of alpha, which are not equal to 0 or 1, such that for every n, you have this. Okay? By the way, everything I will explain today will be useful also for the course on noise sensitivity. So you will see second exercise, we will try to do critical exponents, and some of them are useful for this class as well. Okay. So perhaps the first question to try to understand this theorem is to look at the easiest case you can imagine. And the easiest, yes?
Alpha must be bigger than 1, must be.
No, any alpha will work. So let's try with the easiest example, which is alpha equals 1. So my first question is, can somebody tell me what is the probability to have a black crossing going from left to right in the case of the lozenge? Somebody that didn't see it before. Yeah.
Maybe I saw it.
Ah. No, but, I mean, so if you didn't already saw it, it's okay, because I guess I will not have better. So
1/2.
It's 1/2. So why now? So that somebody who didn't see it before can tell me why 1/2. Yes? Sorry? By duality, yes, self-duality. So what is the dual model in our case? What we will call the dual model in our case.
Switch black and white or not?
Exactly. So that's why percolation, triangular percolation is perhaps the nicest percolation model. It's because it's exactly self-dual. You just have to think that you are Daltonian, or I don't know, but that you don't see red and blue, yellow, but yellow and red. So in this case, how do we use this? We just say, okay, either I have a black crossing going from left to right, or what is the complementary of this event? It's exactly that I have a white crossing from bottom to top. For people that are not convinced by that, imagine you don't have this crossing, and take the most, all the points that are connected to here, take the boundary which is the most on the right. It's necessarily a yellow crossing, and it goes from bottom to top. So this is exactly the complementary event, and this is equal to 1. But as you said, you have self-duality, so the yellow and the red sides are the same. So here I can replace this by a black crossing. And using symmetry, by rotation, I can deduce that this is exactly this probability. So I get 2i's times the probability equals 1. Okay? So it's why you take this losange shape. Yes.
Square lattice will work as well.
Yes. Yes. So everything I explained here for the triangular lattice will work for the square lattice. But somehow this triangular percolation, you will see it's better because we have a conformal invariance which is proven. So I will be able to use it in the first session. But all the arguments I do here with triangular lattice are completely true with square lattice. Bond square lattice, of course, yes, yes, bond square lattice. Okay. So now question 2. Let's assume that we have a crossing. And let's consider the lowest one. So I have my losange, and I take the lowest crossing. Question, can you tell me, so gamma is the lowest crossing. It's a random variable. Can you tell me what is the minimal sigma algebra for which this event is measurable? So gamma is deterministic. I consider gamma a possible crossing curve going from left to right. What is the minimal sigma algebra here in order to... so what are the sites that I need to look at in order to be sure that gamma equals, big gamma equals small gamma or is not equal to small gamma? Okay, so here I have a guess, which is all the guys below my crossing. So I don't know, I had this crossing, small gamma, and if I want to check if big gamma is equal to small gamma, what do I need to do? Don't be shy, I will not send chocolate. Sorry? Okay, so you want all the sites on gamma to be black. I agree. Is it sufficient? Look only at that. No, okay. Why? Because we want the lowest one. So what do I need to check in order to be sure that I have the lowest crossing? Yes. So I need somehow to say this guy, it's below the lowest crossing. So if it's below the lowest crossing, it means that necessarily there is a white path going to the bottom. Because if there is no white path, then it means that I could have done this and I was not the lowest crossing. So in order to check that I'm the lowest crossing, I really need to check a priori all the sites that are below my gamma. But I don't need to check more, and that's the important things. Because now, what is the configuration above gamma when I condition on this event? Yes, that's a percolation of parameter 1/2. Because this event is only measurable with respect to these sites. So I didn't touch to my top site. So above it, it's just a percolation parameter 1/2. Okay. Sorry?
What does it mean it's the lowest? You can do something that starts in the lower point and the lower point but pass above this white path.
It means you have a certain number of crossing. Obviously, when you have a crossing, you never have only one. I mean, there are plenty of ramifications and things like this. But I want to have the one which is the lowest, the closest from the bottom.
Yeah, but did you say that now just checking this vertical white path, you are sure that's the lowest?
Yeah. Yes, if I check for every, so if it's the lowest, all the sides here are connected to the bottom. So of course my picture, so that's the thing with percolation. If you want to understand crossings, you have to think like a crossing. And it's very hard, I mean, because a crossing is nasty usually. So I should have done something like this. This would have been more like the lowest crossing. But I need to check that for all the sides that are below it, I'm connected to the bottom. Okay? Okay, so what I want really to emphasize is that, okay, perhaps I know what is here, but conditionally to that, I know nothing about what is above it. Okay. So now let's try to prove this theorem. So we have already the case alpha equals 1. And if you want to try to tackle this problem with, say, in a naive way, what you are going to say is that, okay, I take n times n and n times n, so 2 lozenges, and I want to prove that there is a crossing. Okay, I take, so this is a case where alpha equals 3/2, and I want to prove that there is a crossing. So what do I do? I mean, first step, you can say, okay, there is a crossing between here and here. And I can do also the same thing with this box and say there is a crossing here. And if they touch, well, I won. But the problem is that there is no reason why they should touch these two crossings. And it's there that you start to imagine why it's a hard theorem. Because, okay, let's carry on and let's take this rectangle and let's consider a crossing. Still don't touch. And I guess I will stop here, but you imagine that if you start only with crossings that are, say, crossings of a lozenge, then you will not manage to plug your crossing together, to combine them in such a way to construct a longer crossing. So here there is a non-trivial argument to try to find. Yeah? No? Okay. So the difficulty is really to pass from this alpha equals 1 to something more, to try to create a crossing which is a little bit longer, a little bit stretched. And the idea, and it's where I did a mistake in my exercises, is that I was thinking about the square lattice and not the triangular lattice. So let's consider this shape. So that's a shape n times n and n times n. And let's consider the lowest crossing from left to right here. And my question is the following. I want to create a path which is slightly longer than just crossing a lozenge. So my question will be, can somebody tell me, give me a lower bound on the probability to connect this? So that's a bad idea, but to connect this part to this part. So I'm not working with a lozenge, but somehow I'm trying to create a path, a long path. So I condition on the fact that this path is the lowest crossing of this rectangle. So I condition. So let's see. 1. So do you have an idea how to prove? So I condition on gamma equals, big gamma equals small gamma. So I'm not allowed in any way to use what is below it. because a priori I discover it already. But all the remaining area of this weird shape, I can use it as much as I want, and as I want. So, do you have an idea how to bound from below this? Somebody has an idea, but yeah?
What if you continue a little bit at the upper, like this?
So, you want to do like this? And on the other side, okay. Yes, and what? A little bit shorter. He's playing with me. But you don't know yet that you have this. So sorry, perhaps it was not clear in my, we don't assume this theorem, we are trying to prove it. So the only information that we have is alpha equals 1. We know that we cross with probability 1/2 here. And I want to cross a little bit longer. So if you want to have a crossing from here to here, you should have alpha equals 2 already, that we don't know yet. So I'm going to help you a little bit. All these arguments for Rousseau-Semmelweis, there are many roads to prove Rousseau-Semmelweis now. But they all involve the same ingredients. And the same ingredients, you can guess what they are. It's independence. We are percolation, so it's independent. And we already use it in the sense that we say it, what is above here, it's a percolation process. So it's not depending at all on what happened below. So independence is the first ingredient. The second ingredient is symmetry. And I will come back to this later, but symmetry is what saves you. You like symmetry. And the third thing is self-duality. And we use it already, but we will use it again. So what can be symmetric here? Perhaps I'll do it bigger. What could be symmetric in our picture? Let's write the symmetric of something. Yeah, the path. So let's take the symmetric of the path, which is not yellow at all, but let's say green. Okay, let's consider this. And I want to prove that this thing is connected to this with a probability which is not going to 0. So let's try to use this. And in order to symmetrize a little bit my domain, I'm going to be nasty with myself and saying I'm not allowed to use this. Okay? It will improve my probability anyway. So let's say, okay, no, I don't like this area. I will not use it. So now I'm really in a symmetric domain, and I want to prove that this thing is connected to this with a probability which is not too small. So does somebody has an idea how to do that? Think to what you did before. Somehow it should not be that different. Sorry? Yes, 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 yes. So if you don't have a path like this, what does it mean? It means that there is a path starting from this part and which is cutting cutting the domain into two pieces. That really goes here. That's exactly the complement. Otherwise, you have a path. But this is exactly the same event. That's the symmetric and with the other color. So these two events, they have the same probability. So the probability to connect this part to this part is larger than 1/2. I have a lower bound. So if you wonder why I'm not writing a lot of things, really everything is written in the corrections. So don't worry about that, but we'll try just to get the idea. But so the conclusion is that if I take the lowest path and I condition about it, the probability to connect this path to this is 1/2, or it's greater than 1/2. So now, if I just consider that, and I look at the probability to connect this to this, I can bound from below this probability by saying, okay, first I enforce the existence of a crossing for the left thing here. So it costs probability 1/2. And after, conditionally to this crossing, I don't know what it is, but I take the lowest crossing, and I know that all this thing is connected to this with probability 1/2. So finally, I really get that this thing is connected to this thing with probability 1/4, at least. Okay? And so this is an argument which is due to Stas Smirnov. That's, I think, the closest argument, the fastest argument you can find for this Russo-Simon-Welch theorem. But let's say that all the proofs that exist, they always involve this kind of reflection of, so that's not true what I'm saying, but all the proofs that looks like this always involve this reflection of the lowest path. There are other proofs by Bolobas and Riordan, for instance, which involve other arguments, but more involved somehow. Okay, so I know that in this weird shape, I cross with probability 1/4. So now let's try to prove that in this shape, I cross with a good probability from here to here. So I want to go back to what I started with. So these rectangles, or lozenges. So somebody has an idea how to prove that you cross with good probability from here to here. Not exactly, because you could imagine, and it's really what they want to do to annoy you, you can imagine that all the crossings are finishing here. So they would get out here from here.
That's the coloring.
Sorry, yeah, I'm very bad at drawing. Okay? So you could imagine that it does this. Okay? So how could you prevent? I mean, you are allowed to pay something if you want. I mean, yes?
So you make another pass from down to up on the right side and use the PT.
Yes. So you could have done exactly the same thing with, okay, so that's really where I stopped to be. Okay, you could have done the same thing in this domain, which is exactly the same as this one, so that you would have a crossing like this. But this time, with these two crossings, you necessarily have a crossing from here to here, because they intersect necessarily. Okay, but what is the probability of the intersection of these two events, A and B? So I know that the probability of A is greater or equal to 1/4, and the probability of, so A is this event, say, and the probability of B is greater or equal to 1/4 also. And I want to estimate the probability of the intersection. So here you need what we call correlation inequality, because these two events are not independent. So you know that when you try to compute the probability of an intersection, if you are not independent, you have basically no way to do it. But in the case of percolation, what Vincent explained this morning is that if you take A and B, two increasing events. So what is an increasing event? In our case, it's just an event if you switch some sites from yellow to red, so from white to black, you remain in your event. The event is stable by adjunction of black sides. So it's an event that likes the black sides somehow. And typically, a crossing is exactly an event like this. You can switch sides from yellow to red. If there is already a crossing, you will keep a crossing. And what the FKG inequality says is that this probability is larger than the product of the probability. And that's not a surprising inequality if you see it that way. Let's divide by the probability of B. It gives you, that's exactly equivalent to say the probability of A knowing B is larger or equal to probability of A. But when you think about increasing events, if you have already B, it means since it's an increasing event, it means that there are already black sides, because really it's what it lacks, this event B, to have black sides. And these black sides, they are going to help your event A. So it's very intuitive that this probability of A knowing B will be larger or equal to the probability of A. Okay, so using this inequality in our case, we deduce that the probability to have a crossing from here to here is 1/16. So, okay, I'm not going to carry on like this too long. Now let's directly do this thing, crossing of a 2n times n rectangle. And the idea is always the same. So you cross like this with probability at least 1/16. You cross like this with probability at least 1/16. But you also cross like this with probability 1/2. So using again the FKG inequality, you can prove that the probability of this event is larger or equal to something which is way too large for me, but larger than this. And it does not go to 0. And that was what was not obvious at first sight. Okay? And really, the key step was to manage to create a slightly longer path. So in this weird geometry, but really that was the main step. Okay? So we have the Rousseau-Semmelweis theorem for alpha equals 2. So now, next question. How do you do, whoa, sorry, how do you do for a rho n times n? I mean, obviously the arguments are close to what Vincent explained this morning, but it's always good to knock 2 times at the same door. So, how do you prove this for any row? I mean, we are not going to do that forever, so let's have a nice argument to deduce from 2 any row.
So if that row is less than 2, then it's obvious?
Yeah, okay. So we have for every row less than 2. And can somebody give me an argument to do larger than 2? Yes? Yes, yes, exactly the same argument as there. So you divide your very long rectangle into pieces that are n times 2n, and you start to have crossings like this. Let's say like this. And you assume that all, so this is obviously, you see it, it's n times n, okay? So, and when you do like this, you create a very long rectangle, crossing of the rectangle. And really, you see the philosophy of the thing in the sense that once you are able to prove a long crossing, then it's very easy to deduce a very, very long crossing if you want. But
why is not going the probability to 0 too many times?
Rho is fixed. Yes, sorry. Rho is fixed here. So the bound will be one of, but Rho stays fixed. So we don't have an idea about what is, so yes, actually we could, but we are not discussing the limit when Rho goes to infinity. Okay. So that was the proof of the Rousseau-Simon-Weil theorem. And really the three ingredients were independence, symmetry, and self-duality. And just an open question, that's always very interesting to have the open question in the field, and you will see it's very frustrating because you have already everything to understand the question. So open question. Okay, let's be at criticality for a side percolation, but not on the triangular lattice, on another lattice. Or let's say even nicer, let's be at 1/2 for another triangular lattice, not the regular one. So for instance, you just change, I don't know, let's change it like this. Now this one has too many symmetries, but something like this. You repeat this pattern infinitely in all directions, so you get a lattice. Prove Rousseau-Simon-Weil for this lattice. And the only thing you lose is you don't have enough symmetry. So of course, here perhaps I did exactly the thing that if you work 10 years, you will manage to adapt this proof for this lattice. But let's say if you don't have any symmetry, we don't know how to prove Rousseau-Simon-Weil. And that will be very important because now you are going to see that I can derive many things with Rousseau-Simon-Weil. And Vincent already gave several examples this morning. So that's a very powerful tool. Yes? I cannot hear you, sorry. Okay, so they don't prove a real Rousseau. So for Voronoi, you say. So for Voronoi, they prove, but using another technique, and still you need, at least in law, a certain symmetry. So you cannot. So what could happen if you don't have symmetry is that all the crossings, let's imagine that all the crossings are going to be ballistic somehow. They are going to all be like this. And you see that you are not going to be able to combine them together. So if you don't have symmetry, we don't know how to rule out this thing. Ready? Okay, so that was the open question. Okay, applications now of this. So the first thing is, now I take, say, an annulus. So I should take, so not this one, but this one. What is the probability to have? So I guess you agree that it's easy now to deduce that there exists a circuit surrounding the origin with some probability not going to 0 and not going to 1 either. So the probability like this of this event, so that was, say, 2 to the n and 2 to the n plus 1. The probability of this event is bounded by some constant, c minus and c plus. So that's the first application. And how do you do that? Vincent explained it this morning. You just cut it in 4 long rectangles, and you use the FKG inequality to plug together 4 crossings. Okay? So this is not very an application of Rousseau-Simon-Weil, but an important step. So now, can somebody tell me why there is no cluster at p equal 1/2? No infinite cluster, sorry. Which is not obvious at all. When you think about it, this p equal 1/2 can be a little bit natural because of this self-duality, I agree. It gives you a good hint that that's the right critical point. But if you don't know how to prove it, even proving that there is no cluster, infinite cluster at criticality, is not easy. Yes? Yes, exactly. So there is not a lot of things to do. So if you want to prove that there is no infinite cluster, it's sufficient to prove that 0 is not connected to infinity with probability 1. Or if you prefer, the probability to connect 0 to infinity is 0. But in any of these analyses, there is a positive probability that there is a white circuit that surrounds the origin, which will prevent the existence of a path from 0 to infinity. So let's say if you look between size 2 to the n and 0, you have even a little bit better than just non-existence of the infinite cluster. You have that the probability that 0 is connected by a black path to the box of size 2 to the n, you have that this is smaller than c plus to the n. Because there is n analysis, and for each one, there is a probability c plus that is not connected. There is a circuit disconnected. So if you prefer, I don't like the 2 to the n. So let's say n. So let's replace this by m. And so it means that here you get something like something like m to the minus alpha, where alpha is some strictly positive constant. So you see, the probability that 0 is connected to the boundary of a box goes to 0, and it goes even fast because it goes like a power of n, at least.
But
yes?
C plus doesn't depend on 2 to the power n, because the distance between 2n and 2n plus 1 is 1.
Yeah, so the first, here it's 2, 4, say, and this one was 4, 8, and so on. So they always have the same shape.
So you're applying the formula in rectangles that are longer and longer.
No. Look, this rectangle, it has always the same aspect ratio.
Ratio, yes.
Yeah, because what is important is the ratio. Okay, but very good question. Sorry, I should have been more clear. So it decays to 0, so there is no infinite cluster, first thing, and it decays like a power of n. Okay. Remember that in the subcritical phase and in the supercritical phase, when you look at connections, it decays exponentially fast, usually. So in the subcritical phase, it decays exponentially fast, and in the supercritical, if you condition to be in a finite cluster, it decays exponentially fast. Can somebody tell me why it's not the case at criticality? It does not decay exponentially fast. If I look at the probability that 0 is connected to the boundary of the box, it's not going to 0. It's not going to 0 exponentially fast in M. Yes? I'm sorry, I have done. So you want sorry, I didn't get it.
If every side has an exponentially small probability of having a crossing from that side,
yes.
summing over one face.
Okay. He's cheating, but that's very good. Yes, that would give you that you cannot decay exponentially fast. That's true. bad. Okay, so I need to, so I will have to, so that's, yes, that's a good argument. I would prefer to have something constructive, but that's a very good argument. So just for people who didn't hear, you say, if it decays too fast, then when I'm looking at my rectangle, each point on the left side has a very small probability to be connected to the right side, because it has a very small probability to be connected to distance n anyway. And if this probability is smaller than 1 over n, for instance, because there is n choices for the left side, then you won't be connected with probability of order 1 to the left side, to the right side. So that's completely true, and it works. But for what I want to do next, I would like to have, can somebody tell me how to create a path from 0 to the boundary of the box using this Rousseau-Semouet theorem in such a way that the probability of this event will be larger than some m to the minus beta. Not necessarily the same beta, but the same alpha, but let's say this bound. Can somebody create for me? Yeah, oh. Okay, which one? Bit. No. So, yeah? So how do you do that? So staircase, yes, the idea is here. So how do you start?
2 by 1, 2 by 1, 2 by 1.
So 2 by 1, okay. So you assume that there is a crossing like this, yes. So what do you do next? Yes. So this is a 2n times n path. So if I keep this width for this rectangle, I can go to 4n, because the only thing I want, if I want to have a probability which is not going to 0 for my crossing, is to have an aspect ratio which is always the same, or at least bounded away from infinity and 0. So here I can do that. So far, using the FKG inequality, the probability of this event is larger than c minus squared. And I can carry on, and so on. And after the logarithm of n steps, I will have created a path from 0 to the boundary of the box. And so here, it would have been c minus to the logarithm of m, which is m to some constant minus beta. So at criticality, is it clear or yes? So at criticality, you do not decay exponentially fast, and even you decay like a power of n. And actually, you have a much stronger result than this one, which is that here. Which is that this probability of connecting 0 to the boundary of the box of size n should behave like this. Some constant plus small o of 1. So the alpha and the beta are the same. And I don't want to give you the c, but we will prove that. We will derive this c. And it's really where they silly enter into the game. And you cannot do it without that. But let's say, so far with the Rousseau-Semouet theorem, I have already bounds. Okay. I guess last question. Does somebody has a better idea of how to prove? So Vincent already gave a clue, but let's try to give even better, further intuition how to prove so we just proved that there is no cluster at infinite, no infinite cluster at p equal 1/2. So it exactly gives you that PC is larger or equal to 1/2. And that's the fastest proof. There is other proofs that are pretty fast, but this one is the fastest one. So you see, it's not as elementary as we wish for. So what we did we prove this. How to prove the other way? So if you want to prove the other way, you want to take P strictly larger than 1/2, and you want to prove that it's supercritical. So you want to prove that there is an infinite cluster. But somehow we have a strategy to create an infinite path. You look at this, and you carry on forever. So of course, at criticality, my lower bound will go to 0, which is normal since there is no infinite cluster. But now, if you hope or that the probability of a crossing is actually going to 1, okay, you have an infinite number of rectangles to cross, but it's easier and easier to do it. And that's exactly the philosophy of the proof. If you can prove that the probability of a crossing at P this time the probability of this crossing goes to 1 fast enough, then the construction we sketched there will work. And so there are different ways of doing that, and none are completely elementary. So I will not prove it. If I'm fast enough, we will have a good intuition at the end of the second exercise. But say the philosophy is to look at the graph of P down the probability of this event, AN, this crossing. So at 0, the probability of a crossing is 0. So it starts like this, and it must finish at 1. Because for P equals 1, of course, you have a crossing. 1, 1. And between it, it's a nice polynomial, so it's going to do something like this. This is typically the graph of this event. And what you know is that here, at 1/2, you are somewhere which is not 1, close to 1, nor 0. And the idea that you will see in noise sensitivity, I guess they will talk about it, is that this kind of event, when n goes to infinity, there are sharper and sharper steps here. So of course not all, but this event here has this property. So I will not be able to explain, I guess, properly, but if you take a bigger n, it will be more like this, and more like this. And you see that when n is going to infinity, if you take P which is greater than 1/2, then the probability are going to 1. And actually when you do that, you can even estimate the speed at which you go to 1, and prove that it goes fast enough to 1 such that this construction constructs a path from 0 to infinity with strictly positive probability. So at the end of the second exercise, we will have the right tool to do that. Okay, so that's all for the Rousseau-Semoe theorem, and now we are going to try to go a little bit further in this kind of arguments. This is called the critical exponent. And for this event, which is called a one-arm event, you have one arm that goes from 0 to the box of size n. So it's the one-arm critical exponent. Okay, if I give you the opportunity to guess for one caipirinha and that you didn't see it, so what is the value of C, I can guarantee that you will not find it. C has a very strange value, and you will see why it's this value later, but if you didn't see it before, you cannot guess it. But you see, I looked at the one-arm event, I could look at other events. For instance, I could look at, say, the probability that there is, okay, so there is a black path and a white path. And it's conjecture that here you have also another critical event, C prime, critical exponent, C prime. That will be the critical exponent for the two-arm events. And same thing, if I ask you what is the value, you will not guess it. But there are some exponents where you can actually know the value for free. Or I mean, at most for free, in the sense that we are going to be able to do it. And these events, they are connected to geometric constraints of your model. So there are two events that I'm interested in. So the first event is the following. So I take the probability, and I take a box of size n, and I look at this point. And I want the probability that there is a black path going from this point to the boundary of the box, of course, excluding this path, this bottom. So here I'm not allowed to finish here, and a yellow path. So that's the two-arm event, but on the boundary. The probability of this, you will see, we are going to prove that that's of order 1 over n. So in other words, the critical exponent here, it's 1. So that will be the first thing we are going to do, and if we have time, I don't guarantee, but if we have time, we will try to prove the following. Now you take in the upper half plane, in the bulk, and you look at the probability that there is a certain number of paths like this. So of course here I don't want them to arrive exactly at 0. It's not possible. There is not enough. Oh, actually, there is enough here. So you want that. Sorry. But let's say if it's arriving at distance 10, it's OK. It will be the same kind of probability. And we are going to prove that this is of order 1 over n squared. So the exponents are very nice. And it's really, you will see, for trivial reasons somehow. OK, so let's try to do the two-arm event on the boundary. So let's perhaps try to. Can somebody give me at least one bound or an intuition how perhaps we could guess this 1, this exponent 1, this 1 over n. Why is it 1 over n? Perhaps that's a hard question, but let's say it, let's put it, sorry?
Because there's only one point like that on.
Exactly. That's the reason. And when I was saying that it's because there are geometric constraints, exactly what I mean. In the sense that, roughly speaking, there is only one such point on the boundary. So you will see that's not exactly true, because you could have two. I mean, this is not excluded a priori. You could have this configuration. 2 points like this will be fine. But that does not happen with very, very good probability. Or at least there is a tight number of such points. So let's try to prove that. So what you said is right. There is only, so philosophically, there is only one point on the boundary, which is like this. So, first question, can somebody construct such a point? Let's prove that there is at least one point with good probability. Yes?
Leftmost crossing.
Yes, that's the intuition, exactly. Yes. But you need to be sure that there is a leftmost crossing and that it's not too much on the boundary. I really want the guy to be in the middle here. Because, I mean, if you look at this critical exponent, it could be different. I mean, obviously it's not a big deal, but I want it to be really in the middle.
But because of single Welsh, you can always take a rectangle.
Okay, so let's say you take these two rectangles, yes?
No, I meant the rectangle centered in the middle.
Center at the middle, okay.
And that's for crossing of it, and the leftmost crossing of it.
So you just consider one crossing and you take the leftmost. But you don't, I mean, the leftmost in this case, probably it will be just this one, I mean, something doing that. But it doesn't mean that here it's not carry oning. But the idea is here, I mean, you are close to it. So how to be sure that this leftmost crossing, it's touching something which is yellow?
As for a yellow crossing, the disjoint rectangle to the left of it.
Yes. So that's the idea. So the idea is to do like this. Let's say you take two rectangles. So here there is a distance n. But I'm just going to take rectangles of width n over 2. And, okay, I say there is a crossing, a red one, and a yellow one here. Now, when I'm looking to the leftmost crossing on this big rectangle, so when I'm looking, at the left side of this cluster, this black cluster, necessarily it will be touching a yellow cluster, a white cluster. So the leftmost crossing of this cluster, it will be exactly adjacent to a yellow crossing. And when you look at the bottom point of this crossing, so perhaps here it's doing like this point here, it has exactly two arms leaving from here, from him, sorry. But so here there is n choices. N choices, so this happens, so the probability of this, it happens with probability c to square, with c is the probability to cross this very long rectangle. So now the probability that there exists a point with two arm events here is c squared. But the probability of there exists is smaller than the sum of the probabilities, and there is n probabilities. So this is c squared. Or, I mean, so this is true, but this is an inequality. So that's smaller than the sum over the n possible points, of the probability to have exactly the two arm event. But just be careful if we want to be completely rigorous. This two arm event, it does not necessarily go to distance n, but it goes at least to distance n over 2. If I start from here, I only go to distance n over 2 a priori. But let's say that this is smaller than the sum, so n times the probability that there is a two-arm event which goes at distance n over 2. So basically, I proved this thing, the lower bound, with c squared over 2. Okay?
So how do you prove that this yellow and red, they merge at the same point? Because the yellow
Okay, so it's not true. I mean, perhaps this one does not merge with this one, but it will merge with some yellow here. Perhaps there is a red one between them. But the leftmost side of this cluster, I mean, you should really see, I guess the best way of not making a mistake here is to say you take the leftmost side of this cluster. And really the leftmost side, since it's the leftmost side, if I do one additional step, I must be on a yellow because I'm the leftmost side, on the leftmost side, okay? So I have one inequality. How do I do the other one? How do I prove that there is of order one guy? Perhaps a little bit more. You see, there is no constraint that is saying there is only one guy. You can have more than one guy. But why, typically, do I get only one point which has two arms? And this is something that will be useful in percolation, which is very useful and which is called separation of arm separation. So I will reformulate the question like this. Can you change a little bit your event you are considering, this one, the probability of having two arms, so that they have the same, almost the same probability that this one, but in this case you really have only one guy which can have this property. You see, you modify, perhaps you will lose, say, 1/1000 in modifying this event, but in this case, really I have only 1 point that can satisfy this. What is the problem in this case? Why can I have several guys, several points that have two arms? It's because they can be just beside of each other. They can be alternating like this. How could I prevent this? Saying if I have this, I cannot have this anymore now. How could I modify this event in such a way? Yes? Exactly. If you can do the following, if you can prove that in this case, actually, so let's perhaps do it here. If you can do that, in this case, there is only one point that can satisfy this. If I'm on this side, I cannot have a red, and on the other side, I cannot have a yellow. So the question now is how to prove that this event is of the same order of magnitude as this event. Yes. So if you want to use also Seymour Welsh, you just have to be a little bit careful about what you saw or not in your configuration. So let's assume that we indeed have two arms like this, but we don't know where it's ending. What you want to do, I guess, is to say, okay, let's do Rousseau-Seymour Welsh here. I have a crossing, and the probability that there is a crossing from here to here, it's bigger than the probability to have a crossing from here to here. And do the same thing here. That will cost me two constants, but only two constants that I will not fall below. So it will give you two constants, and so if this is of order, say, 1/n, this will be still of order 1/n. But the thing is that you have to check that this area is unexplored when you want to use Rousseau-Seymour Welsh. So how can you guarantee that the event of having two paths, it's not measurable with respect to what is, you don't need to measure what is outside these two crossings somehow. Exactly as what we did for Rousseau-Seymour Welsh, we had to prove, so we had this lowest crossing, but in order to plug things to consider this new crossing connecting, we first had to check that that was a percolation process above my path. Here it's a little bit the same thing. I agree we are going to use Rousseau-Semmelweis, but we need to check that what is here is also a percolation of parameter 1/2. So how do you check that? How do you check that that's percolation of parameter 1/2? So exactly as, so let's look back at the lowest crossing. One way of checking that that's the lowest crossing is to do the following. You start a small robot here, he's happy, and this guy, he has a left hand and he moves and he follows always on his left, he leaves black sides. And this robot, when he is going to perform his journey, he's going to discover exactly the lowest crossing. And what he will have measured, what he will have discovered, is exactly the sites. A priori, I don't know how many sites, but I'm sure that sites that are below the lowest crossing. Can I do the same thing here? Can I have a small robot that will discover my two arms and let what is outside free? Nice percolation process. So the answer is yes, and I guess you are just too shy to say what it is, but imagine I'm going to pay 1/4 to assure that here I have a red site and here a yellow site. And now I start my robot here, and I tell him, be careful, you just let the black site or the red site on your left and yellow site on your right. So what this guy is going to discover your rectangle, and because there is two arms, he's going to finish here. And what he will have discovered is only red sides on his right, and yellow sides on this left. So he will have discovered exactly the interface between your two arms, but nothing more. He didn't discover anything outside of it. So what is outside, it's a percolation process. I use Rousseau-Semmelweis. I get that the probability of this event is of the same order as the probability of the two event. But here I have only one such site which can be in this configuration, so the probability is necessarily smaller than 1/n, because otherwise I would have more than one site. So this is the case, so this is how you prove this. And you see that really the arguments are elementary, it's using geometric constraints. So how do you do that? And I will do it a little bit faster, but that's the same philosophy. Or perhaps I can ask, I mean, somebody knows how to create such a cluster, such a point? So that will be exactly the same thing. What we are going to do is prove that there is of order 1 site with 5 arms, like this. So does somebody has an idea how to create? Yes, does. Okay. So am I late or? No, that's okay. Okay. Sorry, I already forgot when I started. So how do you create such a site? That's the same thing. Let's do the same philosophy as here. Let's assure that there is a crossing like this, and that there is a crossing here. Okay? So I know that there is that. But now what I'm going to do is that I'm going to start from here, my robots. Perhaps I have more than one robot now. And I'm going to discover the first interface between these two, between a white and a black site. There is one interface necessarily where I already have the two guys, the two paths adjacent one to the other one. And when I'm doing that, I only discovered what is below this interface. I don't know what is above it, so that's a percolation again. What I can do is I can use Rousseau-Simon wedge on, say, this very narrow rectangle to guarantee that there is a path. No, a path like this. This point exactly has 5 arms. I constructed one. Not much complicated than the other thing. In the other direction, what you can do is to guarantee this. You can guarantee that up to some constant, you exactly have this configuration. And when you think about it, you can have only one of these. Okay. So that was for the 2-arm event, and for the 1-arm event, for the 2-arm event on the boundary. So yeah, it starts to be just useless. I would just like to finish with what we call the 4-arm event, because that's a fundamental one, and you will need it for, I mean, perhaps not, but that's always good to know about it. So we know the exponents for these events, so now we are going to look at this one. So Vincent introduced it this morning, the 4-arm event like this. He told you that that's the pivotal points, in the sense that if you switch the state of this site, you have a crossing that direction or that direction. And what I want to prove, and he sketched the proof this morning, is that there are many such points. But saying that there are many such points, it's somehow equivalent to the following thing. It's proving that the exponent is strictly smaller than 2. If the exponent is strictly smaller than 2, let's say 5/4, then you will have a lot of such points, because they have a probability which is much larger than 1/n squared, and there is n squared possibilities. So what I just need to do, I will not prove that it's 5/4, but I'm going to prove that that's smaller than 2. I mean, sketch the proof. There are many ways of doing it, but or perhaps I have time to prove it. Okay, no. I guess that's the end of the day. So the idea is to prove that that's easier than the 5-arm event. The 5-arm event is obviously harder than this and has critical exponent 2. So if I'm able to say, okay, this is much easier, and by easier I mean there is an n to the alpha difference between both, then I will have won and prove that alpha is smaller than 2. So this event, I'm just going to say that if I look at this thing, so that was yellow. This is a 5, and here intersection, I mean, I'm going to put a big O, and I'm going to explain what it is. But the 5-arm event is exactly that. I have 4 arms plus 1 arm, but 1 arm which is different from these 4 arms. We say that it occurs disjointly. And the thing is that when two, so that's definitely not the most optimal proof, I'm sorry, but I guess that's the most efficient, the fastest one to explain. When you have two events like this that are disjoint, the probability of the intersection of these events is smaller than the product of the probabilities. So I'm going to conclude, and after going, I will go back to this, what I just said, because it can look a little bit weird. And here, I have this, and this. Did I put it the right way? Yes. Okay. So it means that this probability is larger than this probability over this one. This is of order n to the minus 2. And this is of the order n to the minus alpha for some alpha. It's what I proved with Rousseau-Semmelweis. I told you that the one-arm event, I don't know how to compute it, but I know that it exists. It's somehow in the sense that it's not 0 or 1 or infinity, or 0, 1, infinity. Sorry. Okay, so you know that this is smaller than n to some alpha, and this is larger to n to the minus 2. So you get that this is larger than, so perhaps, yeah. No, so I guess you need this like this. Yeah. So you deduce that this is larger than n to the minus 2 minus alpha. So the exponent is smaller than 2 for this 4-arm event. Okay? So just what I didn't explain is this weird inequality that says if you take two events that occur disjointly, then the probability of the product is less or equal to, the probability of this intersection is less or equal to the product of the probabilities. And that's a weird correlation inequality somehow. It's not as intuitive as the FKG inequality. But you should understand it in the sense I have less room somehow. Okay, I have this event that occurred, and now I need to find this, but I cannot be helped by any of these sites that I already discovered to perform this event. So I have less choices, less entropy somehow. And so it's the reason why. So that's called the Reimer inequality, and that's far from being easy to deduce. So if I was a little bit more careful, I would do a little bit of work to have only to use the BK inequality for people who know it, which is the same inequality for increasing events. And that's already much easier to prove. And I mean, it's not very hard to do some work in order to just have to use this. So don't be afraid by this inequality. But that's the fastest way. Okay. Just to finish now, let's try to prove or to give you a better hint of why PC equals 1/2. So we take P. So what we want to prove is that probability of a crossing, say, n times 2n goes to 1 when n goes to infinity and even fast. So this is an event that we call AN, say. And as Vincent explained this morning, knowing how this probability evolves in P, it's somehow looking at the points that when you switch them, because between P and P plus DP, you are going to switch very few sites. And when DP goes to 0, basically, you switch only one site in your configuration. So when you look at the derivative of this probability when P, so the derivative with respect to P, it will be exactly governed by these sites that alone can make something. Because if you need two sites to make something happen, in your derivative, you will disappear because you are too expensive to have two sites that will occur and switch. So really, you are governed by these sites alone that switch. And these sites alone that switch, that's exactly these sites. So the derivative here, as Vincent explained, is really connected to the number of sites that are pivotal. And here, perhaps I will not explain exactly how you do that, but everything I did here, it's not necessarily true it can be true away from p equal 1/2 if I have Rousseau-Simon-Wesch. If I know Rousseau-Simon-Wesch, everything I did after the proof was true. And I would get exactly that this is of order n to the minus 2, this is of order n to the alpha, and so on. So if Rousseau-Simon-Wesch is true, I get all these estimates. So in other words, if an is between 0 and 1, not too close to 0, not too close to 1, then all the estimates I did are true. And when you think about that, it's not very surprising here to get the following form if I had a little bit more time and I wanted to do it properly. What I would get here is something that I say I have Rousseau-Simon-Wesch in the sense the probability of an is not close to 0, is not close to 1. It's exactly what it means. You can imagine another form, but let's say something of this form times exactly what I compute here, so the number of pivotal points, which is n squared, times their probability, which is n to the minus 2 minus alpha. And so this is of order n to the alpha. So, of course, here I just move my hands and it's perhaps not very convincing, but what I want to say is that the derivative, it's not surprising that at the end you get something with probability of an, 1 minus probability of an, which is basically saying you have Rousseau-Simon-Wesch, and once you have Rousseau-Simon-Wesch, this thing, you know how to compute it, and you know that that's not very small. That's of order n to the alpha. Okay? So you have something which is of this kind. You have f prime of p, which is greater or equal to f of p, y minus f of p times some n to the alpha. And this, when you integrate it, say, between 1/2 and p, you will get exactly that f of p is larger or equal to 1 minus exponential to minus n to the alpha or something like this. But let's say, so perhaps I'm not used with that, so I don't want to, let's say this. But so here it's really a very elementary step to integrate this between 1/2 and p to get this estimate, which is exactly saying I'm crossing my rectangle with larger and larger probability. And typically what you get is this kind of things. This is so actually in this case you get a little bit better, but usually you get that. So now when you do your construction by rectangles, remember that your rectangles, they double of size every time. So what you want, what must be convergent is this thing. 1 minus the size of a rectangle, and the kth rectangle would be of size 2 to the k, and power minus beta, sorry. And this is convergent. This is really convergent. That's a product, obviously convergent. So strictly positive, which means that I constructed a path from 0 to infinity with strictly positive probability. So of course I did like very huge steps here and here, but the philosophy is really here. Your pivotal points, they are saying that close to 1/2, you have this very narrow window. But so you will hear much better explained in other course, I guess. I will stop here. Thank you. No, but I mean, thank you, but. Okay, I'm not sure it's very.
Jaka